you for that nice introduction and for having me here today. As Bally mentioned, my name is Troy Hanlovic, and I'm joining you from Amgen in Thousand Oaks, California, to discuss in silico map separation spaces for green method development. Let me get my pointer ready. Okay, so I'm a member of Amgen's synthetic separations team, which is a group of separation scientists, and we support all small molecule separation science from early discovery through discovery, which is where we spend the majority of our time, and then all the way through commercial stages on special projects. And on the left, you see our most recent group photo from this summer, where we took this photo at our headquarters in Thousand Oaks, California. And then on this side of the slide, you see some of our workflows that we do on a routine basis. The majority of our time we spend in purification support, whether that be achiral or chiral purifications or the high throughput purification platforms, from the microgram all the way to the multi-gram and occasionally the 100-gram scale. Besides purification, we do method development, analysis, and characterization for a variety of different applications, such as chiral analysis, achiral analysis, polar surface area measurements, solubility, log-D, and etc. So today we'll spend time talking about method development and in silico modeling, and for the specific application of greener, more efficient method development. So we are a high throughput lab, and since we're a high throughput lab, we take a more brute force approach, not as targeted as the nice talk that we heard earlier. And when our samples are submitted, they automatically go through a screening protocol, which is typically multi-tiered with 16 columns in tier 1, and multiple mobile phases or modifiers. After this automated screening protocol, we look through the data and choose the column and mobile phase combination that provides the most suitable chromatogram. So this is our initial starting point. It's all gradient screening on a standard 5 to 95% gradient for reverse phase. And then from there, we do method refinement, adjusting the gradient settings, column temperature, etc., until we end up with our optimized analytical method. Now, we also do a lot of preparative chromatography, and I'll show some data from that today, where we have a similar approach of first we do screening, either in reverse phase, SFC, or normal phase. Then we develop isocratic or focus gradients and optimize our cycle time and loading, and then we can do our prep. So with prep, we have different considerations since we're mostly interested in isolating a single peak of interest, and we're not so worried about peak-to-peak separations of the other components in the chromatogram. And since today's topic of the symposium is digitalization of R&D, I'll spend some time discussing on the next few slides how we could add chromatographic simulations and in silico modeling to our workflows to do greener, more robust, and more efficient method development with not as much experimentation. So this can work for both the analytical and the preparative scale, and as I mentioned before, I'll show examples from both. And although we did hear some of the simulation earlier, I'll just give a quick crash course on that. So our standard modeling protocol is a gradient temperature model where we do 3 different gradient times, typically, again, from 5 to 95% organic in 3 different times at 3 different column temperatures. We like to try to encapsulate the separation space that we're going to work in. So if we know that the column can go up to 60 degrees Celsius, for example, we will set a range from 60 to 10 so that we can interpolate inside the separation space instead of extrapolating. So we kind of adjust these parameters on a case-by-case basis. And then this gives us a look at the entire separation space for that separation, which I'll show you. We then take this data and then put it into ACD's LC simulator, which forms relationships between the amount of organic in the mobile phase and temperature, as well as some other parameters, which I could show you. And we then have an output of a mapped separation. So we look at the resolution maps, we choose our desired conditions, and then we end up on our optimized method that serves a certain goal that we could then experimentally validate. So forward here. On the left, I'll show an example of a resolution map, and this is a resolution map where we're plotting the %B of the starting gradient versus column temperature. There's a variety of different things that you could plot on these resolution maps, as well as different times. So here we're looking at the initial timing conditions, and then you see on the color bar what is the axis critical resolution, which is the resolution of the least resolved pair. And the nice thing about these separation maps or the resolution maps is that we're able to look across the conditions instead of just at discrete points. And we see here that areas of orange offer baseline resolution of the critical pair, while areas of blue show overlap. And the nice thing about that is it allows us to track the peak crossovers. So if we were to click on area A here, we would get the chromatogram of the conditions at area A. And then you could see that the peaks are in the order of 3, 4, 5, the critical peaks. But as we go to B, we cross over these blue lines. So I believe you have 4 crosses over 5, and now we see that the order is 3, 5, 4. And likewise, if we were to go to C, we see that the resolution or the peak order is 5, 4, 3. So by building this model, it's inherently green as we're using only 9 experimentations for the case of the gradient temperature modeling. And we're able to track all of our peak orders and make methods that are really strategically developed without doing a lot of experimentation that would be necessary for the traditional method. You can go past 2D optimization, so we could add temperature, time, and pH, for example, or temperature, time, and solvent ratios. This requires more than those 9 experiments, but it does allow you to do simultaneous optimization of multiple parameters. And if you're interested in that, our group lead Imad and his co-authors have several publications on that that are shown down here in the bottom. But we'll stick to temperature and time for today, or temperature and isocratic composition. And again, the really nice thing about using the in-silico modeling is the holistic look at the separation space. So this is an example that I like to show because it was kind of surprising to us. So it was a compound that was submitted to our lab from a discovery project, and we knew that it had 3 main components from the mass spec of the solution. But after multi-tier gradient screening using different gradients, different mobile phases and columns, we tested over 100 different conditions. We were never able to baseline resolve the 3 components. So what we did is took the column that provided us the best resolution, which was actually a vancomycin-based column. I'm showing the stationary phase on the bottom. It's quite unique for an achiral separation since this is a chiral stationary phase. And that provided 3 peaks with a split peak on the 2 and 3. So it was able to resolve 3 out of 4 components. We then added that into the in-silico model, and the output said that a simple isocratic method would be able to separate the 4 main components. And we were kind of surprised by this because we never saw that. But if you look at the map, you see that there is a very narrow region of resolution. So only in between really 20 to 22% of your acetonitrile in this case are you able to separate these 4 components. After that, the 2 peak and the 3 peak start to co-elute, so they cross over each other. And if you didn't build this model, you wouldn't really guess to test this very narrow region here. And you can easily skip over that in your screening protocols since it's, a unique area. And after we ran it, we saw that the model did match the experimental data. And there's actually this 5th peak that we didn't even know was there that was quite substantial. So that was really nice. And it goes to show you that by mapping these separation spaces, we can look at very specific regions that you wouldn't easily guess from your screening protocols. And in this case, it didn't take a multi-step gradient or anything complicated. It's a very simple 9-minute isocratic method. So I always like to show this example. And with that, let's switch gears into green chemistry. We'll discuss a little bit about green chemistry and then tie back the in-silico model into the green chemistry with some distinct scenarios. So before I give thoughts on green chemistry, I like to define it since it's a newer field of chemistry that came out in the late 1980s and 1990s. And most people point to the definition of the field from this book called Green Chemistry Theory and Practice, which was written by Paul Anastas, who's considered to be the founder of green chemistry. I have here the father of green chemistry, and his co-author, John Warner. And in the book, he defines green chemistry as the utilization of a set of principles that reduces or eliminates the use or generation of hazardous substances. So we can make our methods greener by reducing or eliminating the use of hazardous substances, as well as some other considerations that I'll show on the next slide. And I always like to include this quote of his on the few pages later in the book, where he says, green chemistry is not complicated, although it's often elegant. So very small changes in your analytical methods can make large changes to their sustainability and impactful sustainability-driven decisions, which is really useful from these small little changes. A newer construct of green analytical chemistry came in 2019 by PM Nowak, but it's also important. It's called the RGB, or the red, green, blue model of green analytical chemistry. And what Nowak said in this model that's now very popular is that we cannot just consider an analytical method's greenness. As analytical chemists, we have information to gather, or material to deliver or purify. So if a method's very green and say it produces no toxic substances and uses very little instrument power, but it doesn't give you the desired information, that's not useful for our goals as analytical scientists. So we also have to consider analytical performance, which he assigns to the color red, and productivity and practicality, right? We can't make a method that's very impractical or not very productive, even though it's green, since that'll slow down our workflows and cause a bottleneck situation. And the ideal method, therefore, is in the middle. I have represented by this star, where we balance greenness, productivity and practicality, and analytical performance. Now, when we consider analytical performance as separation scientists, we usually have a good idea of how we can measure performance. It may be through these parameters that I showed there: selectivity, resolution, retention, efficiency, and so on, that we all calculate on a daily or regular basis. We also have ideas about productivity and practicality, right? We can look at runtime, the amount of loading, the robustness of the method, and reproducibility. And these are all routine as well and well understood within the field. But how we quantify greenness is a little bit more ambiguous or obscure, since this is a newer construct. So I'll briefly get into that before I show some of the examples of using in-silico modeling for green method development. So green analytical chemistry metrics have been a popular area of research in the last 20 years, I would say, and there's lots of them. So on the left is a figure from Mike Hitt's 2022 review paper, where he shows all of these different acronyms that represent different metrics to measure the greenness of just a liquid chromatography method. And they all consider different aspects and different parameters to the greenness. And it kind of makes things confusing because you don't have a straightforward, metric like resolution that we all understand. I don't even know what some of these acronyms stand for, and I've been doing this for a while. So to address this, the ACS Green Chemistry Institute formed a pharmaceutical roundtable that contains most of the major pharmaceutical companies across the world. And in 2019, they put out this AMGS calculator, or the Analytical Method Greenness Score, that considers different characteristics from all these different metrics in a single, easy-to-use, open-access calculator. So you can go on the AMGS website, I encourage that you do, and add your method details, and it'll give you a single score. The lower the AMGS, the greener the method. And within that single numerical score, you see three different components. The instrument energy score, so faster separations tend to be greener as they use less time on the instrument. Solvent energy score, so greener solvents such as those that are bio-derived are better than ones that take more energy to create and dispose. And the solvent EH&S score, the environmental health and safety score. So you could go in there and kind of take a look at what is driving the greenness of your method and see where you can make improvements. And we'll show some examples of the AMGS as it relates to in-silico modeling in the end. So as I mentioned before, now we'll tie together the green analytical chemistry that I discussed with the in-silico modeling, using some scenarios that we thought were useful or came across in our time at Amgen. So the first scenario is the banning of fluorinated solvents. This actually just came up at lunch yesterday, and people are talking about it often. So the European Union has proposed legislation. You could read this 224-page proposal that was released last year from the European Chemicals Agency to ban fluorinated compounds. They proposed the banning of roughly 12,000 chemicals. And this all relates to per and polyfluorinated alkyl substances, or PFAS, and they're known now colloquially as forever chemicals due to their extreme environmental persistence and toxicity. And one PFAS that separation scientists use often, that might not really think about it as a PFAS, is trifluoroacetic acid. And this is one of the most commonly used and also most high-performing reverse phase liquid chromatography additives, especially in peptides and protein separations. So what we wanted to do is see, can we use the in-silico model to move from trifluoroacetic acid to something that would not be banned by such legislation if this legislation was to pass in the EU or potentially here in the United States. And we chose this example because we wanted to do a twofold improvement. Here we have 11 peats from a forced degradation solution. This is the best chromatogram from our screening protocol. And we wanted to see, can we replace the TFA that produced the best analytical results with something that's not banned, so a greener alternative, and at the same time resolve these co-eluting peats. So we see peats 3 and 4, 9 and 10 are co-eluting from the mass spectrums, and our critical resolution is 0. So to do that, we replaced the TFA with trichloroacetic acid, which would not be banned if PFAS got banned. And we built our model, and here we look at the resolution map of the PFAS-free separation space. We see that there is some resolution at that bottom right quadrant. And then we chose a condition from this map after just those 9 experiments. And we were able to now move our critical resolution from 0 to 1.4. So we see it's almost baseline resolved. 9 and 10 are just slightly overlapped, as well as 6 and 7. And we're able to remove the PFAS. So this is greener and higher performing at the same time. Alternatively, we can move to use the in-silico model to replace less desirable or less green solvents with more green solvents. Outside of improving our method's greenness, we could see scenarios like this if we have shortages of chemicals, such as the 2008 great acetonitrile shortage that we had in the US. And as a high throughput lab, we need to be able to quickly substitute our solvents in these cases to keep delivering information. And often when we move from traditional solvents such as acetonitriles to greener solvents such as alcohols or carbonates, we find that these greener solvents are lower performing, and that's because there's a reason that we were using the traditional solvents in the first place. So in this case, we chose these 6 analytes that are used to represent different reverse phase liquid chromatography retention mechanisms, and we replaced the acetonitrile with a greener methanol. We built a model, and we see that the in-silico model shows us 2 regions there at the bottom where there's resolution, and we were able to then replace the methanol with the same critical resolution, 1.59, in a shorter time period, so that's also good for greenness. Now you do note, even on this simple substitution, so we're still staying on the same column and it's still reverse phase, from acetonitrile to methanol, we see that there is a change in peak order for even just 6 peaks. So originally we have 1, 2, 3, 4, and now we have 3, 2, 1, 4. So using the in-silico model really allows you to track how these peaks are migrating and easily do assignments in a way that's not so easy with traditional experimentation. And then the final scenario I want to discuss today is one that relates to preparative chromatography. So this was a sample that was sent to us from one of our sites in Asia, where they had a desire to isolate a peptidic API dimer to use as an analytical standard. The sample that they sent us had 3 main components: the peptidic API, the dimer, and an impurity, and they only wanted the dimer. And we were able to develop a method that separates the 3 main components easily in around 6 minutes from our standard screening protocol. But we saw as we did the mass overload study that it becomes very difficult to collect that dimer as it's directly in between the API and the impurity. And this shows you that purification can be difficult even if an analytical resolution is good. So what we wanted to do is see if we could build a model that allows us to manipulate the peak order and produce a more productive method that requires less replicates and is therefore greener. And what we saw from our 3x3 screen and then our model is that there is this area of orange, which is where our original method was, and a blue stripe indicating peak crossover. And then up here, we see that there was a predicted different peak order. Now, the problem with this is that that's a long gradient. So we're going from our 5-minute gradient to an 11-minute gradient. That's at a high temperature, which isn't really desirable for preparative chromatography. So what we did is build a focus gradient, and through adjusting the method on the model using our computer assistant method, we saw that the model said that we don't actually have to run a full 5 to 95% gradient as we were doing in our screening protocol. And instead, we could run a very shallow 54 to 56.5% organic gradient. And if we run that very shallow gradient, we could reverse the peak order of impurity in the dimer and put the dimer all the way to the right by itself. And now, as we're loading, in this case, 2.5 times more, and we could probably even go above that, we see that it's very easy to collect the desired fraction. And all of the other peats in the front are not really to be concerned with as they're eluting before our desired fraction. So if we increase our loading by greater than 2.5 times, we're doing 2.5 times less replicates, and that's a much greener option. And before I finish, I want to discuss maybe something that we'll see in the future, and that's using these green analytical chemistry metrics, which I discussed before, such as the AMGS here, as a parameter during our method development. So on the left, we see our traditional resolution map that comes from the LC simulator. And what we were able to do with that information is build actually a map that, instead of plotting resolution or critical resolution, is plotting the greenness of the methods, or the AMGS. And you see that the greenness ranges from above 25, which is not very green, to below 5, which is much greener, a 5-fold difference, depending on where you're operating within the separation space. So this we call a sustainability map. And by looking at where we have resolution on the left and where we have greener methods on the right, we could choose one of these 4 methods that all produce adequate resolution, so above 1.5. And you see that if you were to choose method A instead of method D, which both provide, above 1.65 critical resolution, a 5-fold difference in greenness. So you're able to strategically pick greener areas of the sustainability map without doing any extra experimentation, which is really nice and something that we hope becomes more routine and potentially commercial in the future. With that, I'll give my conclusions and a green chemistry method roadmap. So first, you have to understand greenness, how it applies to your lab. If you don't understand where you can make improvements in your method greenness, it's very difficult to make those improvements. You also have to know the goal of the method, right? We have to consider the productivity, performance, and greenness, right? So we make the greenest method that achieves our desired goal. We then can show that we can limit experimentation through computer assistant method development. So by using just these 3x3 screens, in this case, 9 experimental runs that are all standard, don't require any tweaking, we could develop very interesting methods that I showed today. We could also search for alternative solvents, additives, and stationary phase combinations using in-silico modeling and make that a really facile process. And we could optimize the productivity by using peak crossover strategically, as well as speed analytically, to make the greenest and highest performing methods possible through this limited experimentation. And that's all really enabled by the in-silico modeling. And with that, I would like to, before I take questions, thank my 2 main co-authors on this work, Dr. Ahmad Hadar Ahmed, who's our group lead, and Dr. Doipayan Roy, who was my supervisor during some of the time that I did this work, as well as the remainder of my co-authors that are shown on the left, and our function lead, David Bauer. And also some of this work that I discussed today was work done during my time at graduate school at the University of Texas. So I'd like to thank my advisor, Professor Daniel Armstrong, and my colleague there at the University of Texas, Dr. Farouk Wahab. And with that, I'll take questions.